right. So let's discuss about alternating series. And of course, we'll also discuss about absolute convergence and conditional convergence. Now see, you're already aware of what a series is, right? Series has infinitely many number of terms. And sometimes, they may have positive terms and some of them may be negative also. But in particular, you see, if the series has, terms of this kind, the first term is positive and the second one is negative. And the third term is again positive and the fourth term is again negative. So like this, alternately, if you have positive and negative terms, then we call it as alternating series. It's not for sure, here in this case, I have taken the first term as positive, but in general, the first term may start with a negative sign also. But the thing is, alternately, we must have positive and negative terms. So when you have a series with such terms, we call it as alternating series. But in particular, understand, though we have different signs here, you must understand when the signs are already mentioned here, individually, if you take u1, u2, and so on here, they must all be absolutely positive, right? I mean, if you take u1, u2, excluding the signs, if you take only u1, only u2, only u3, they're all positive. But when you take them in a series form like this, you can find their signs alternately. For the first term, we have positive sign. Then for the second term, we have, negative sign. Then positive sign again, then negative sign again. Like this, when you have alternate signs to different terms, different positive terms, we are calling it as what you call an alternating series, right? Now see, you can find some examples here. Look at them. One, look at the first one here. 1 minus 1 by 2, then plus 1 by 2 square, then minus 1 by 2 cube. If you write it in general, we can write it like this. You see, we are quite, comfortable with this kind of series. We can write something it like this. When you look at all these terms, one part is clear, 1 divided by 2 to the power of n. This is your nth term, right? In fact, you can understand in the first term, it is 1 here. So probably you can even take it as, because if you want to start n from 1, you can even take it as n minus 1. Right? So if you now take n is equals to 1, it becomes 1 by 2 to the power of 0, which comes out as 1. Then when you take n is equals to 2, it becomes 1 by 2, and then n is equals to 3, it comes out as 1 by 2 square, and so on. So here summation starts from n is equals to 1 to infinity. If you want to start it from 0, you can take it as 2 to the power of n. Anything is all right. Now, then see, we need to get what you call a positive sign for this. So alternately, to get positive and negative terms, we need to take it as minus 1 to the power of something. So initially, we should get what you call, positive sign, right? So when you take n here, then when you take n is equals to 1, it becomes a negative sign, right? So just to leave that, I'm just taking it as n minus 1, because you see 2 to the power of n minus 1 is there, no? To get that, again, here also I'm taking it as n minus 1. So when you take n is equals to 1 now, it becomes minus 1 to the power of 0, which comes out as plus 1. So positive sign comes for the first term. Then when you take n is equals to 2, it becomes minus 1 to the power of plus 1. So that, you will get a negative sign to the second term. So like this, you can anyway identify the nth term for this series. Because alternately have sign changes, we are calling this as an alternating series. Similarly, if you look at this, here directly nth term is given to you, right? So for different values of n, clearly all the terms are mentioned here. See, for the first term, we have now negative sign, and then you see we have the positive sign, then again negative sign, and so on. So it is also an alternating series. But see, for more clarity, they have taken minus common from this, so that the first term starts with positive sign here. It's not absolutely necessary every time. You can just understand whether it starts with a positive sign or a negative sign. If you have alternately sign changes for different terms, then we can call it as simply an alternating series, right? So that is such a simple definition you can understand. Alternating series is of course an infinite series in which we'll find alternately sign changes, right? First, let us say first term has positive sign, then automatically second term must have negative sign, and then again positive sign, then what you call negative sign. Like that, if you have alternate sign changes, then we'll call it as an alternating series. Now again, the question comes, when you are given a series, we are always testing whether that series is convergent or divergent, right? We had seen for a regular series, by using what you call nth partial sums. By calculating nth partial sums, we had verified whether the given series is convergent or not. Right? How we defined it, if you recall, when this sequence of partial sums, when this sequence of partial sums is convergent, I mean, when n tends to infinity, if the limit of Sn approaches to a finite value, then we said, the given series is convergent. Then we have discussed about what you call series of positive terms. For a given series of positive terms, using different, of course, this is also for given series of positive terms only, but without calculating the sequence of partial sums, without calculating the series of positive terms, I mean, without calculating the series sequence of what you call partial sums, we have discussed three different methods, like what you call comparison test, then D'Alembert ratio test, and then N-through test. Using those three tests, we had to find out what you call convergence of a given series of positive terms. Now, in a similar way, when you are given an alternating series, we need to see whether the given series is convergent or divergent. But see, in many cases, when you have this minus 1 to the power of n in your series, right? We had seen some problems of this kind also. More or less, this series goes to divergence. I mean, it becomes actually oscillatory, right? Now, in such a case, we need to give a definition for this, right? We are just modifying the basic idea of this, and then we are moving it this way. Look at this. Now, in this case, when you are given an alternating series, we are following the test proposed by Leibniz, right? So we are calling it as a Leibniz test. And what we are doing here, you see, when you are given an alternating series like this, u1 minus u2 plus u3 and so on, and if this series is such that un plus 1 is less than or equals to un, as we discussed a few seconds ago, you see, when you are given a series of this kind, individually, if you take these terms u1, u2, u3, we have already understood, these are all actually positive terms, right? Anyway, we are ignoring the sign here. Already the sign is considered in the series itself. So we are simply ignoring the sign when you are looking at only these terms, right? So these four terms, or else, you can write as many as you want. These are all what you call only positive terms. And if these terms, are in this way, u1 is greater than or equals to u2, then u2 is greater than or equals to u3, then it is greater than or equals to u4. And in general, somewhere you will find nth term un, right? This un is greater than or equals to un plus 1, and so on. Understand, when you consider only these terms by ignoring the signs, if you found this series as, I mean, this sequence of terms as what you call decreases, if this is a decrease, if this is a decreasing series, right, without considering the signs, then if that series also, if the nth term also converges to 0, right, limit n tends to infinity un, if it is also 0, then we say the given series is convergent, right? When you are given an alternating series, by ignoring the signs, we are only looking at the different terms here. And if those terms are in decreasing order, along with that, if the limit of nth term as n tends to infinity is 0, then we say the given series is convergent, right? So this is one simple idea what we are using to find out whether the given alternating series is convergent or not. Okay, in many cases, as we had seen already, when you are given an alternating series, it goes to diverge. It diverges actually. Look at it, as n tends to infinity, when this limit doesn't exist, automatically, it's a divergent series. When the limit exists and if it is particularly 0, then only we are saying it is a convergent series. Okay, that's a story. And now, when you are given an alternating series, using this simple idea, I mean, we'll verify whether these two conditions are satisfied or not. By verifying these two conditions, we'll decide whether the given series is convergent or not. Okay, so that's a simple thing. Now let me just take this question. Test the convergence of this series 1 minus 1 by 2 root 2 plus 1 by 3 root 3 minus 1 by 4 root 4 and so on. Now let's look at this solution carefully. One thing you see before going ahead, understand this is clearly an alternating series, right? This is clearly an alternating series. Now, when it is an alternating series, you can just recall those two conditions, I mean, from Leibniz test. Right, so I'm just writing this. the given series. I'm just writing it for more clarity, because in the examination you can expect a question on this alternating series. 1 minus 1 by 2 root 2 plus 1 by 3 root 3 minus 1 by 4 root 4 and so on is an alternating series with, can you expect what may be nth term here? Look at it this way. With un is equals to, look at all these terms, ignore the signs for time being, ignore the signs and only look at the nth term. So when you look at that, it's clear when it is first term we have exactly 1. And in the second term, if you look at it, 1 by 2 root 2, then it is 1 by 3 root 3 root 3, then it is 1 by 4 root 4, in that sequence, one can easily expect nth term will be 1 by n root n, right? Just ignore what you call that sign and understand this. Right. Therefore, you can understand now un is clearly what you call 1 divided by n root n. Fine. Now see, when you are given an alternating series to follow Leibniz test, what conditions we need to verify? The first condition is it must be a decreasing series, isn't it? It means uh, so it means un plus 1 must be less than or equals to un. So anyway, we are just trying to compare these two, right? So when un is this much, we can easily understand what is un plus 1. Un plus 1 will be, now I'm just replacing n by n plus 1. So that it is 1 divided by n plus 1 times what you call square root of n plus 1. Fine. Now, so now let's just compare these two, whether un and un plus 1. I mean, whether un plus 1 is less than or equals to un or not. When un plus 1 is less than its previous term, definitely we can say it is a decreasing series, right? And that holds for all n also. Before proceeding further, I'm just writing this one. Look at the denominators of these two terms. When you look at the denominators, you see here we have n root n, and here it is n plus 1 into root of n plus 1. Clearly, n plus 1 is more than n, as we know, right? For any integer n, n plus 1 is clearly more than n, and even square root of n plus 1 is also more than square root of n. So that the product in the denominator here, so that the product, what it is, n plus 1 into square root of n plus 1. This will be surely more than, this denominator, n root n, right? Clearly, this denominator, square n plus 1 into root of n plus 1 is more than n root n. As this is true, when you take their reciprocals, what happens? It is 1 divided by n plus 1 into root of n plus 1. I'm just taking the reciprocal. So when I take the reciprocal, you see the sign, this relation will be completely changed. When it was greater than earlier, now it becomes, less than. So when it is 1 by n plus 1 into square root of n plus 1, right? This will be absolutely less than what you call 1 by n root n. So this implies, you can understand now, this is nothing but un plus 1, and it is clearly less than, nth term un, and this holds for all n belongs to capital N. Right? So the first condition is now verified already. You see, when you are given an alternating series, we are actually verifying two conditions, and now the first condition is already verified. Now, what is our second condition? We need to take what you call limit of un as n tends to infinity. So after writing this, you can understand, as we already discussed, the terms are, the terms in the series are decreasing. So this is one condition what you are verifying. And now let's consider limit n tends to infinity un. For the nth term, let's see what happens to the limit as n tends to infinity. So this is equals to limit n tends to infinity un. How much is un? You see 1 by n root n. It's absolutely clear. You see, when n approaches to infinity, this denominator completely approaches to infinity only. When the denominator approaches to infinity, this 1 by infinity approaches to absolutely 0 only. There is no question about that. So hence, right, see the two conditions are satisfied. The two conditions of Leibniz test are satisfied now. Hence, I'm writing that by Leibniz test, Leibniz, Leibniz test, the given alternating series is convergent. That's it. So when you are given an alternating series, right, without calculating the sequence of nth terms, sequence of partial sums, I mean, right, we are just using this Leibniz test to identify whether the given series is convergent or not. Understand, when you are given an alternating series, if any of these two conditions are not satisfied, what are those two conditions? First one is un plus 1 is less than un. I mean, the terms in the series must be in decreasing order. When the terms in the series are decreasing, then you're also verifying one more condition. What is that? Limit n tends to infinity un is equals to 0. If these two conditions are satisfied, you are saying it is convergent. If even any one of them are not satisfied, then you can say the series is not convergent, or you can even simply say it is divergent. Okay, that's the story in the case of what you call alternating series. Right, look at this question now. Test the convergence of the series summation n is equals to 1 to infinity. Look at now this, you are given actually what you call the nth term here directly, right? Understand this, when you are given nth term and when you take different values for n, as you can see here, for n is equals to 1, it becomes minus 1 to the power of 0. So it is positive. And for n is equals to 1, it is 1 divided by 2 minus 1. So we got that simply 1. Then when you take n is equals to 2, when you take n is equals to 2, we'll get it as minus 1 to the power of 2 minus 1. So it is minus 1 into 2 divided by 2 times 2, 4, 4 minus 1, it is 3. That's how we'll get it as minus 2 by 3. So that the second term here is minus 2 by 3. Now when you take n is equals to 3, you can understand it, minus 1 to the power of 3 minus 1. So it is minus 1 whole square, which is plus 1, into, if you substitute n is equals to 3, it becomes 3 divided by 6 minus 1, 5. So it is plus 3 by 5. Like that, if you take n is equals to 4, we got it as minus 4 by 7 here. Clearly, the sign is changing alternately. That's how you are calling it as an alternating series. And remember, when you are given an alternating series, as I told you till now, we simply ignore that sign. You may have positive sign or negative sign. We only take what you call this un by ignoring this sign. I mean, n by 2n minus 1 is the only un here. We don't consider what you call this sign. Whatever minus 1 to the power of n minus 1 you have, we ignore that. By ignoring that, we compare the terms. And if you get those terms in increasing order, right, we'll proceed further. So see here, it's clear. Un is n by 2n minus 1. Right, clearly un is n by 2n minus 1. Now similarly, if you calculate un plus 1, un plus 1 means you need to replace n by n plus 1. So if I write n is equal to n plus 1, and even in the denominator also, what you get here, you see n plus 1 remains as it is in the numerator, but in the denominator here we have 2n plus 2 minus 1. So 2 minus 1 is plus 1, that's how we got it as 2n plus 1 in the denominator. Therefore un plus 1 is n plus 1 divided by 2n plus 1. Right, now we are actually verifying whether un plus 1 is less than un or not. That's how we'll get the decreasing order. So to get this, let me take the difference of those two. Un plus 1 is un plus 1 minus un. So what you have un plus 1, it is n plus 1 divided by 2n plus 1 minus, in the nth term un, see we got it as n divided by 2n minus 1. Now see, to simplify this, we have taken what you call the LCM. So if you take LCM, it is product of these two comes in the denominator, 2n plus 1 into 2n minus 1. We take what you call a kind of cross multiplication, n plus 1 into 2n minus 1 minus n into 2n plus 1. Right, kind of cross multiplication like this. Then you see we get this term. Now to simplify this, see what we are doing, n into 2n. Right, see I'm just multiplying these two terms here. N into 2n, it is 2n square. then n into minus 1, 2n square. See, we are doing it like this. N into minus 1, it is actually minus n plus this 1 into 2n. It is plus 2n, 2n minus n. So we got it as n here. Then if you multiply the constants, 1 into minus 1, which is minus 1 here. Right? So we got these three terms. Then here we have, minus. That minus is carried as it is. And when you multiply this n with these two terms, n into 2n, it is 2n square. Then n into 1, it is n. So we got these total terms in the numerator. So when you look at the denominator here, it's just like, 2n plus 1 into 2n minus 1. Correct? 2n plus 1 and 2n minus, it's like a plus b into a minus b. So we can just take them as a square minus b square, which is 2n whole square, 4n square minus 1 square is 1. Right? Now, if you simplify this, you see, this 2n square and here it is minus 2n square. You can just cancel them. And here it is plus n. When you multiply this minus inside, we'll get this as minus n. That can be cancelled. So what left here is, you see, only minus 1. So that minus 1 is coming, it is there in the numerator. And this is 4n square minus 1 in the denominator. Understand, n is absolutely more than 1. Of course, in a case, it may be 1 also. N is clearly greater than or equals to 1 because n takes all in what you call natural numbers. So when n is clearly what you call a natural number, 4 into n square will be definitely more than 1. Correct? N is absolutely more than or equals to 1. So 4 into n square will be more than or equals to 1 only, definitely. Therefore, whatever you get in the denominator, that will be positive, and even anyway, that is first of all positive. Right? Clearly, this is positive because 4n square is more than 1. And when this denominator is positive and the numerator is negative, we have a minus sign here. You see, numerator is negative. Clearly, we say this is negative only. Right? Clearly, that is negative only. Right? What you got now by looking at this? So what you got here is this. You see, we have actually taken the difference here. You see, the difference is un plus 1 minus un. And we got this difference as less than 0. When the difference is less than 0, you can understand, you see, if you send un to the other side, we can understand un plus 1 is less than un. Somebody is asking me, why are we subtracting, sir? See, the idea is when you are given an alternating series, we are trying to verify this condition, whether un plus 1 is less than or equal to un or not. That's a question. Right? We need to verify, in fact, two conditions. First condition is whether the terms are in decreasing order or not. If they are decreasing order, we'll verify the second condition. What it is, whether the limit of nth term is 0 or not, as n tends to infinity. So to verify these two, we are taking the first condition here. To verify this, whether un plus 1 is less than or equal to un or not, I'm taking the difference. I cannot directly verify it, That's how I'm taking the difference. And if that difference is less than, see, to verify 2 is less than 3 or not, what we do, we take the difference between these two, 2 minus 3. If this 2 minus 3 is less than 0, we'll say 2 is less than 3. In a similar way here also, to verify this condition, I've taken the difference. And as the difference is clearly less than 0, we can say un plus 1 is less than un. And therefore, we can say the terms are decreasing. When the terms are decreasing, I'm verifying now the second condition. What it is? Limit of un as n tends to infinity. As we know already, what you call un is this. What is un? N divided by 2n minus 1. Now for that term, I'm taking limit as n tends to infinity. So directly I cannot substitute the limits, you see. I'm taking n common from the denominator. So when I take n common from the denominator, you see, you'll get it like this. We have already n in the numerator. And now in the denominator, if you take n common, we'll get it like this. N times 2 minus 1 by n. So this n can be cancelled, That's how we got it as 1 divided by 2 minus 1 by n. Now as n tends to infinity, this 1 by n approaches to 0. Therefore, in the denominator, we'll get it as 2 minus 0. And therefore, the limit is 1 by 2. Recall, if you want to use Leibniz test, we need, the series has to be series should satisfy two conditions. What are those two conditions? The first one is the terms must be decreasing. Yes, that is okay. That is satisfied. But we want the second condition. What it is? Limit must be equal to 0. When the limit is equal to 0, then only we say the given series is convergent. Right? So when the series, when the limit is not equal to 0 here, we can say the series is not convergent. When the series is not convergent, you can understand because it is an alternating series, we can say it is oscillatory. Of course, it is divergent, but as a special case, you see, you can also say it is oscillatory, right? Because of this minus 1 to the power of something, we are saying it is oscillatory. That's how we can just verify whether this series is convergent or not. In case, remember, if this limit is 0, if you get this limit as 0, we would have said, the given series is what you call convergent. As the limit is not equal to 0, we are saying it is not convergent. I mean, it is oscillatory. Now, see, if you look at this question carefully, the series is x by 1 plus x minus x square by 1 plus x square and so on. Now, can you expect what may be the nth term? You see, we have x power 4, or else in the first term we have x power 1 and the second term x power 2, then x power 4 in the fourth term and so on. So you can expect, you see, in the nth term, it will be absolutely x to the power of n only, right? In the nth term, it will be absolutely x to the power of n only. So when it is x to the power of n, in the denominator also, we see we have the same term. That too, we are adding a 1 in the denominator additionally. So that it's clear when you ignore the signs, un is clearly x to the power of n divided by 1 plus x to the power of n. So when that is un, next we need to take what you call un plus 1. Right? When it is un plus 1, we need to replace n by n plus 1. You see, that's how we got it as x to the power of n plus 1 divided by 1 plus x to the power of n plus 1. Right? So now these two are un as well as un plus 1. Now, again, when you are given an alternating series, the condition what you are trying to verify is whether the terms are decreasing or not. I mean, you need to verify this condition, whether un plus 1 is less than un or not. So to verify this, we are again taking the difference, you see, un plus 1 minus un. If you get this difference as less than 0, then you can say they are decreasing. So I'm taking the difference here, you see, un plus 1 minus what you call un. So that I'm just substituting, you see, un plus 1 is x to the power of n plus 1 divided by 1 plus x to the power of n plus 1 minus un, x power n divided by 1 plus x power n. As we did in the previous case, here also I'm taking the LCM only. Right? So when you take LCM, you'll get this as the denominator as usually. But in the numerator, you see, again, we are taking the what you call a kind of cross multiplication. X to the power of n plus 1 multiplied by 1 plus x to the power of n. Then minus, because we have a minus sign here, we are taking now these two, product of those two, x to the power of n into 1 plus x to the power of n plus 1. Right? Now see, if you take these things, what you'll get here, you see, if you take product now, x to the power of n plus 1 into 1, x to the power of n plus 1, the first term, then x to the power of n plus 1 into x to the power of n. You see, the same is written here. X to the power of n plus 1 into x to the power of n. Then minus, if you take product like this, minus x to the power of n into 1. See, it is x to the power of n. Then minus into plus. See, we have minus x to the power of n into x to the power of n plus 1. Right? Looking at those terms carefully, look at the second term and then the last term. These two are absolutely same, you see. We have the same term, x power n into x power n plus 1, but the signs are different. Since their signs are different, we can just cancel these two terms. So then what remains? X power n plus 1 minus x to the power of n, and of course the denominator is quite same. Now from the numerator, you see, x to the power of n plus x to the power of n can be taken out. So when you take x power n common from the numerator, you see, we'll get it as x power n into x minus 1. Right? When you take x power n common from this, we'll get it as x power n into 1x remains here in the first term. So that x comes, and then here it is only 1. Now see what you are given in the question. The value x, the variable x lies in between 0 and 1. So here you are given 0 less than x less than 1. Understand, when x is less than 1, what happens to x minus 1? When x is less than 1, what happens to x minus 1? It is clearly less than 0 only. Since x minus 1 is less than 0, we are writing all this as less than 0. There is no other way. Because, remaining all are, see, x is clearly positive because it is more than 0 and less than 1. X is clearly positive. When x is positive, whether it is x power n or x power n plus 1, definitely the remaining all terms are positive only. except all those, only if you look at this x minus 1, x minus 1 is the only term which is negative here. That's how we take this product as completely less than 0. Now see, this term, when it is less than 0, we can understand un plus 1 is clearly less than what you call un. Let's see what you have here. Un plus 1 minus un is clearly less than 0. Since it is less than 0, from that we can understand un plus 1 is less than un. So that the terms are clearly decreasing. So first condition is satisfied. Then what about the second condition? We need to take the limit. Right? As n tends to infinity, what happens to this? You need to understand. What can we do? You see, nth term is clearly x to the power of n divided by 1 plus x to the power of n. Now see how this limit will be 0. You need to take, again, x to the power of n common from them. I mean, it is this limit n tends to infinity. You can keep this x to the power of n as it is, but from the denominator, if you can take x power n common, what happens? You see, x power n comes out, but in the denominator here, it remains as 1 plus 1 by x to the power of n. So these two can be cancelled out, So what remains? 1 by 1 plus 1 by x power n. But as n tends to infinity, this x power n goes to what you call infinity only. So that this 1 by x power n approaches to 0. As n tends to infinity, 1 by x power n approaches to 0, and therefore you see, see what you are given here. Here it is actually x lies in between 0 and 1. So when it lies in between 0 and 1, it's not no need to take this x power n common, You are given 0 lies, x lies in between 0 and 1. When x lies in between 0 and 1, x power n, when n approaches to infinity, x power n approaches to 0. I hope you remember 0.1 whole to the power of 2, then 0.1 whole to the power of 3. If you take higher powers to this 0.1, will these powers go towards 0, isn't it? That's how when x lies in between 0 and 1, higher powers of x will approach to 0 only. Since as n tends to infinity, x power n approaches to 0, the limit approaches to 0 here, right? But for a regular thing, when x is more than 1, when x is more than 1, certainly the limit approaches to 1. But in this case, since you are given x is in between 0 and 1, this limit approach to 0. If you directly take x power n common from this, we'll get the wrong thing. But that is not allowed here because x lies in between 0 and 1. So as x lies in between 0 and 1, x power n approaches to 0. Therefore, the limit is 0 here. And since the limit is 0 and as both conditions of Leibniz test are satisfied, we can say the given series is what you call convergent.